Okay, in this video we're going to start talking about differential equations and some ways to go about solving them. Now, a differential equation is really nothing more than you being given the derivative of some kind of expression. For instance, so if I'm looking right here, and if I'm given an expression that has dy over dx in it, or any kind of differential expression present, that is considered a differential equation. Now, we have already worked our way through solving differential equations when we were going through the process of finding the antiderivatives. Through the process of finding the antiderivative or an indefinite integral, we have worked our way, and the expression we would get would be considered a general solution to whatever that expression is. It's considered a general solution because we would end up with this plus c on the end, the constant of integration, which means that if I'm looking graphically, anytime I ended up with a general solution, I created a family of functions where, depending upon what c is, that our general solution would represent any of these possible graphs here. Now, this is just for a general equation, but depending upon what c is, I could be any of the graphs that are listed, or possibly even more that's not inside of the viewing window. Now, if we were given an initial condition, or an initial value, that means we're given a point that lies on the curve, which would allow me to solve for c and say, okay, out of this whole family of functions of general solutions, c had to be -2, and so we were going to be this particular graph here. All right, so let's do an example. Let's find the general solution to f of x is equal to the indefinite integral of 3x squared dx, and then find a particular solution that satisfies the initial condition that f of 2 is equal to -3. Well, I'd start by first finding my antiderivative of 3x squared, which the antiderivative of 3x squared dx would be x cubed plus c. So there's my general solution right there for f of x. General solution because we have the plus c. So that's my general. Now, to get my particular solution, I'm going to use my initial condition, which says that I would need to put -3 in for f of x, put in 2 for the x, and then solve for c. And we do that, and we get c to be -11, which means that our particular solution would be x to the third minus 11, and that's the particular solution based on the initial condition, that point f of 2 being -3. Now, as I said before, differential equations are expressions that have any kind of derivative present in them, and they're not always very easy. In fact, we can have differential equations that are in terms of more than one variable, and we see two examples here. Now, it's important to pay attention to what order differential equation we're looking at. Now, I'm looking at this is a first order differential equation because I'm dealing with the first derivative. And this second one is a second order differential equation because I'm dealing with the second derivative. Now, solving differential equations are basically working our way backwards to find the original function and to try to determine what equation has the given derivative. Now, it's important to consider that not all differential equations are solvable by using certain algebra techniques. The first technique that we're going to look at is to solve differential equations by using a method of separation of variables, which is basically, if I'm given an equation, a differential equation, I want to move everything y related to one side and everything x related to another side. And then after I do that, we're going to integrate both sides. And then we're going to use an initial condition if we have one to solve for c. And then we would have our solution to the differential equation. So let's look here at an example. Let's solve the expression, the differential equation, dy over dx is equal to 3 times y. And we're given the initial condition that y of 0 is equal to 1. Well, the first thing that we would do, all right, so I'm going to rewrite the problem here. I get dy over dx is equal to 3 times y. Is I want to get all of my y's on one side and my x's on the other. Well, I would divide by the y and then multiply by the dx. So I have dy over y is equal to 3 times dx. Now we would want to integrate this. So I'm going to integrate both sides, find the antiderivatives. Well, the antiderivative of dy over y is the natural log of the absolute value of y. And I have equals, and I'm going to put the plus c on the x side. So the antiderivative of 3 dx would be 3x, and then I have plus c. All right, now from here, we wanted to go through and write this as y equals. And so I would take off the natural log by rewriting this as y is equal to e to the 3x plus c power. Now we have 3x plus c, so you you add exponents when you multiply like bases. So I could go through and rewrite this and say, all right, that's the same thing as y equals e to the c power times e to the 3x power. Well, c being a number to be named later means that I could treat e to the c power as that number to be named later and write this as y is equal to c times e to the 3x power. So here is a general solution to this. Now, we're going to find the particular solution based on this initial condition, which says, all right, when you put in 0 for x, you have to equal 1. So we're going to put that in. So we have c times e to the 3 times 0. And we solve, we wind up getting c to equal 1. Which means that our particular solution here, our actual solution would be y is equal to 1 times e to the 3x power. All right, let's look at another example here. So the acceleration of a body moving along a coordinate line can be modeled by a of t is equal to cosine. So this is my acceleration function. And the velocity and position functions, or we want to find the velocity and position functions if we are giving these two initial conditions. So I got two initial conditions here. So the initial velocity is -1 and the initial position is +1. All right, well, if I know that my acceleration is equal to cosine, velocity is going to equal the antiderivative of my acceleration function. So we would go find our antiderivative of our acceleration, which is, all right, so we have cosine of t dt. The antiderivative of cosine is sine. And so our velocity expression would be v of t is equal to sine of t plus c. Now we use the initial condition that my initial velocity has to be -1, so I'll put -1 in for v of t, put in 0 for t, and solve for c. Well, sine of 0 is 0, so c is equal to -1. So our our velocity expression for this body that's moving would be v of t is equal to sine of t minus 1. So there's the expression for velocity. Now we also wanted to find our position. Well, position is the antiderivative of velocity. And so we would integrate our velocity function to get our position equation. So position would be the antiderivative of sine of t minus 1 dt. We go integrate that. Antiderivative of sine is negative cosine. Antiderivative of 1 is t. And then we have plus our constant of integration. Now we use our initial condition to solve for c. So my initial position is 1. I put in 0 for all of my t's. And we go solve for c. Well, cosine of 0 is 1. So I have 1 is equal to -1 plus c, which says that c is equal to 2. And so our position equation, we plug everything back in, is going to equal negative cosine of t minus t plus 2.